The longest building in the whole world is called Burj Khalifa. It is rated 829.8 meters tall. But how long would it take for you to slope Burj Khalifa in a state of weightlessness if you were put in an elevator? To calculate that, we are going to deploy Newton's equations of motion, and we are going to first use the third equation of motion, that is v squared is equal to u squared plus 2as. Before we find out the time, we are going to first establish the final velocity we would want to reach the ground with. But for matters of safety, we are going to first subtract 20 meters from the 829.8, and we assume that we are going to start from top and move for 809.8 meters. Therefore, we are going to leave a balance of 20 meters before reaching the ground, such that we can later on use those meters to decelerate and reach the ground with zero velocity. So v squared is equal to u squared plus 2as. Since we are moving from 0, u is going to be our initial velocity and will be 0. Therefore, v squared will be equal to 0 squared plus 2 times the acceleration due to gravity, which is 9.81 times the 809.8 meters. That will bring us to a final velocity of 126.0486 meters per second. Therefore, after establishing the final velocity, now we are going to calculate for the time. How long would it take for us to move through a distance of 809.8 meters, accelerating at an acceleration equivalent to the acceleration of gravity? Using the first equation of motion, which is v is equal to u plus at, we are going to substitute for the values. And you find out that the time taken for us to move through that distance at an acceleration equal to the acceleration due to gravity will be 12.0498 seconds. So therefore, it takes 12.0498 seconds to feel a state of weightlessness as we are sloping the longest building in the whole world, that is Burj Khalifa. Okay, cool. If you're new here, my name is Ario Seth, and on this YouTube channel, we discuss, distill, and break down more insightful, fascinating physics ideas and tech ideas. So welcome to the Physics Club, where we are going to discuss what is weightlessness and how the ISS and the satellites stay in orbit without falling towards the ground. Okay, cool. What is weightlessness? Weightlessness is an apparent state of not being acted on by gravity. You feel you still have mass, but you feel you have no weight. So in this video, we are going to discuss more how does it come about, and one of the other scenarios where you can feel this state of weightlessness is in a vomit comet. Now, there is a program that is used to train astronauts and is called a vomit comet. This is where aeroplanes fly high in the sky and then start moving in a parabolic manner. As they move through the steps of the parabola, they move at an acceleration due to gravity, and therefore the objects inside, including the people who are inside, feel a state of weightlessness. They don't feel their weight. On the other hand, let's also talk about how the ISS, or the International Space Station, stays in its orbit. Okay then, but before we talk about how satellites stay in their orbit, let us first know what is gravity and what brings about gravity. In 1687, Isaac Newton suggested that there is always a force of attraction between two masses in the universe, and that force of attraction is directly proportional to the product of their masses and inversely proportional to the square of their distance of separation. For example, if you consider two bodies, the Earth and the Moon, those two bodies exert a force of attraction between themselves, and that force is equivalent to the product of the two masses, the mass of the Earth and the mass of the Moon, and inversely proportional to their distance of separation, and that is the separation between the Earth and the Moon. Still, on the other hand, there is a force of attraction between me and the Earth, and that force of attraction is equivalent to the product of my mass and the mass of the Earth, and inversely proportional to the distance of separation between the mass of the Earth and my mass. Still, on the other hand, this doesn't stop on bigger bodies. It also works on smaller bodies. For example, this mouse and this cock. There is a force of attraction between these two bodies, which is equivalent to the product of these two bodies and inversely proportional to the distance of separation of these two bodies. Whereas the force of attraction may actually not be appreciated here because these two bodies are very small. But if bodies continue to be larger and larger, for example, the Earth and my body, the resultant force is also very huge. There's a graph that shows how the gravitational force of a body varies as the distance goes far and far. I'm going to project it on the screen, you can see it. So as you're at the center of the mass, the resultant gravitational force is 0. But the more you go away from the center, the gravitational force goes on increasing and increasing until you reach the point where the radius of the mass stops. Now after that point, if you continue moving away from the mass, the gravitational force of the body goes on decreasing exponentially, but it will never decrease up to 0. And the reason is that mass still has an effect on you. But you may ask yourself, if I get out of the earth, will I be less attracted to the earth? Yeah, true, you'll be less attracted to the earth, but now probably you'll have entered another gravitational field of some other object, probably like the moon, and so the moon will pull you closer to itself. But note that the gravity of the earth won't be acting on you. So therefore, there is always a myth associated with gravity and gravitational thing, that there is a point where you reach and there is no gravity working on you, which is actually not true. So I wanted to first tackle that, then I also talk about how satellites stay in their orbits, how the International Space Station stays in its orbit without being attracted to the Earth. Okay, cool. As Newton was explaining this, he also used some analogy, and it's the one I want us to use right here. Consider throwing a cannonball with your hands. If you take a deep look at the trajectory it makes, you'll find out that it makes a parabolic trajectory. Now, consider throwing it harder. You'll also find out that it takes the same trajectory, but it takes longer to be attracted towards the Earth. Okay, cool. Let's go on a high building like Burj Khalifa and throw that cannonball still, using maybe another system that is stronger than us. And you'll find out that it follows the same trajectory, but now it will describe some curvature that is nearly identical to the curvature of the Earth. Okay, cool. Now suppose we put our body in a rocket and go with it in space, and then throw that body with a very strong speed, and we see how it will be attracted to the Earth. You'll find out that it will still follow the same trajectory and it will be attracted to the Earth, but as it is being attracted to the Earth, it will continually miss the curvature of the Earth because its trajectory is following the same curvature. Therefore, this is the same way how the International Space Station is able to stay in space without falling towards the Earth. This is because it is still attracted towards the Earth, but its curvature or the trajectory it follows is identically equal to the curvature of the Earth, so it continuously misses the ground of the Earth, the surface of the Earth. So that is how space stations are kept in orbit without falling onto the ground. Okay, cool. Now let's find out the math behind this thing, behind the trajectory of a body and the curvature of the whatever. Now, this body is actually not being acted on by only gravity. I want us to be clear with that. Now let's do some math here. Okay, not math, but some experiment here. Let's consider this to be like a ball and this is a string, okay? Okay, any mass and this is a string. And if I try rotating, if I set this thing in rotation, you may actually observe that this body is not being attracted here, attracted to the center of the rotation. Why isn't it being attracted yet the string is pulling it? Okay, and you also find out that this body is also not getting off the string. Why? Because there are about two forces acting on this body. There is a force that keeps it in rotation and the force that keeps it attracted towards this. Therefore, this string is going to act as the gravitational force, and the force that keeps this body is called the centrifugal force, okay? For this body to keep in motion without being attracted to the center of the rotation or being plucked off to go anywhere else, these two forces must be equal. The gravitational force and the centrifugal force must be equal for the body to stay in rotation. The same thing applies to the International Space Station and the satellites. The force due to the attraction of the Earth must be equal to the force that is keeping this satellite in motion. Therefore, if those forces are equal, the satellite continues in continuous rotation until its velocity is maybe reduced. Now, let us discuss more about these two equations. M is the mass of the satellite, and V is the velocity at which the satellite is actually moving. Then R is the distance between the center of the rotation, which is the center of the Earth, up to the point where the satellite is rotating from. But as Isaac Newton was describing this cannonball analogy, he said that you must project the cannonball in an area where there are no air molecules. For example, in space, because air molecules would impose a drag force on the cannonball and it would later on momentarily lose its momentum and velocity, thus being finally brought back to a velocity equal to 0. But the International Space Station moves actually at a distance of 400 kilometers in the sky. That is a very close distance, and at that point there are also still some air molecules. That means that the drag force caused by the air molecules still acts on the International Space Station. So how does the ISS combat this challenge? Now, the International Space Station loses 0.1 miles per hour or 5 centimeters per second of velocity each day due to this decelerating effect of the air molecules at the height of 400 kilometers, and also loses a height of about 330 feet. That is also about 100 meters. But to compensate for this, once in every month, the International Space Station fires its thrusters again in order to regain its lost velocity and its lost height. Therefore, that's how it maintains to stay in its orbit without being attracted back to the center of the Earth. Now, if you're still watching up to this point, I thank you for your time. I'm sure you gained a lot from this conversation, and I hope to bring more fascinating and insightful conversations like this. Tell me whatever you have learned or you would like to know more in the upcoming videos, such that I can make research more about them. And I want to thank you for watching. Please consider subscribing if you haven't. If you have liked this video, you might also be interested in the video I made about why aeroplanes fly at high altitudes. It's going to be linked right here, and feel free to check out videos in my physics club. There are a lot more there. I also have a playlist called the Tech Club. It also has a lot of videos. Please feel free to check them out. Thank you for watching. See you next time.